Okay, so it's a great pleasure to welcome to the Congress Maryna Viazovska from Lausanne, and she's going to talk to us about magic functions for sphere packings and energy minimization, which I'm very much looking forward to. Over to you, Maryna.
Yeah, so thank you very much for the introduction. And so maybe I would like to start my talk on a bit philosophical note. So the title of this conference is Unity of Mathematics. So what unites mathematics? And of course, we all know that people unite mathematics. And so that's why on this Congress, we are celebrating the Michael Atiyah and his contributions of people like him. They do unite mathematics. And also, of course, mathematics is united by ideas. And I think one more thing which keeps mathematics together is the mathematics itself. Because mathematical objects, I think they do exist in their somehow Platonian world of ideas. They exist on their own, they have their own life, but sometimes they let us people to discover some of their properties, to study them. And so today I would like to speak about two exceptional objects like this, which somehow they come in different incarnations into different parts of mathematics. And so these are the E8 lattice and the Lich lattice. And so I will tell you to talk today about these two objects somehow from my point of view, from the point of view of their optimality properties. And so I would like to start with introducing the E8 lattice, but maybe one thing I want to say that if at some point of my talk you have any questions, you can of course interact me and ask me, and I somehow would like, so it was very nice to see a live talk just before mine, so it would be, even over internet, it would be nice to have a human interaction. And so the E8 lattice, it's a lattice in 8-dimensional Euclidean space, and it is the unique even and unimodular lattice in this space. And so here, even it means that if we compute the length of any vector in this lattice and take this number squared, then we will always obtain an even integer number. And so unimodular, as always, it means that the co-volume of the lattice is 1. And so this lattice E8, it comes up in many areas of mathematics. For example, E8, it's the root lattice of the E8 root system. Also, because E8 is a even lattice, so we know that its shortest vector has length square root of 2. And for dimension 8, this is a rather big number. And we know that the shortest vectors of the lattice E8, shortest non-zero vectors, there are 240 of them, and they form a kissing configuration in R8. It means that if we take one sphere about 0 with radius 1 over square root of 2, then this 240 spheres with centers at the shortest vectors of E8 lattice, they will be touching this inner sphere simultaneously, and at the same time they will not, they will only touch, at most touch each other, and they will not intersect. And also another thing we can do with E8 lattice, so we can now consider a union of balls with centers at the lattice points and radius 1 over square root of 2. And then we know that such a balls, they will only touch each other and they will not intersect. And so what the configuration of balls which we will obtain, it is called the sphere packing. And it turns out that this sphere packing is the densest one which is possible in dimension 8. And so this is the result we have proven together. So I've proven in 2016. It is that the E8 lattice is gives us the densest packing in dimension 8. And also another property which this lattice have, and I will explain this property in a later slides, it is that the E8 lattice, it's also universally optimal. And it means that it's optimal not only for the packing problem, but also for a variety of energy minimization problems. And so this is a theorem we have proven together with Henry Kohn, Abhinav Kumar, Stephen Miller, and Danilo Radchenko in 2019. And so Leech lattice, it's a lattice which, it's again an even unimodular lattice in dimension 24. And Leech lattice is, so we know that in dimension 24, we have 24 different lattices up to, even a unimodular lattice is up to an isomorphism, so-called Niemeyer lattices. And Leech lattice is the only of these 24 such that its shortest non-zero vector has length 2 and not square root of 2. So all other 23 Niemeyer lattices, they have shortest non-zero vector of length square root of 2. But Leech lattice, it skips this first possible length. And this, of course, makes Leech lattice a very good candidate also for for kissing configuration and for packing problem. And so now the Leech lattice, it has a slightly bigger number of shortest vectors. So it has this like 196,560 shortest vectors. And these vectors, they form a kissing configuration in dimension 24. And it was proven by Vladimir Levenstein and independently by Adlishko and Sloan, that this kissing configuration is an optimal one in the sense that we cannot have kissing configuration in dimension 24 with a bigger number of spheres. And again, for Leech lattice, we can also consider the corresponding sphere packing. So now we are considering all vectors in the Leech lattice, and we consider balls of radius 1 with centers at all these points. And because minimum length between two points in lattice is 2, so we know that these balls, they will not intersect, and therefore we'll have a sphere packing. And it turns out that this sphere packing is the densest possible in dimension 24. So it means that any other configuration of non-intersecting unit balls, it would cover equal or smaller portion of the 24-dimensional Euclidean space. And together, also the joint work with Henry Kohn, Abhinav Kumar, Stephen Miller, and Danilo Radchenko, we have proven that the Leech lattice, first, that it is the densest sphere packing, and also we have proven that Leech lattice is also has this property of universal optimality.
Sorry, can I just ask? I've forgotten what universal optimality means.
Yeah, but that's because I did not tell you that yet. So I will tell you this a bit later.
Thank you.
But it means that it's optimal solution for a big range of energy minimization problems, and I will specify those problems a bit later. And
another question.
Yes.
So you start with the lattice, so you have some sort of periodicity.
Yes.
So does your results about the density apply to possible packings that would be completely aperiodic, not related to a lattice?
Okay, so in our paper, we work with periodic configurations, but then somehow it's not easy to see that if we have any like that the sphere package, so that somehow every density, it can be at least it can be approximated by periodic. If we suppose that we have some aperiodic configuration with certain density, then somehow, as I know, we cannot guarantee that we will have a periodic configuration with the same density, but we can have periodic configurations with density arbitrarily close to this one. And so if we prove some bound, which is true for all periodic configurations, and here like periodic does not mean lattice configurations. So periodic, it's a more general term. So actually being a lattice configuration is rather restrictive condition. And because we can take somehow as like thinner and thinner lattices, it means our lattices with bigger and bigger co-volume, it means that essentially what we can do, we can approximate any configuration with some periodic configurations. And so in this sense, it's sufficient to prove this for periodic, the statement for periodic configurations. And so now let me have this slightly wider look on packing problems. So suppose that we have some metric space, like a metric space here. So here M is the space and rho is a metric on this space. So then we can ask a general question. So how many balls or row balls with respect to this metric rho of given radius can be contained in our metric space M? And then, of course, if this space is compact, then this is just about counting the number of balls. And if M is not compact, like Euclidean space, then we have to give more careful definition and to define it like certain notion of density of our configuration. And so here's another version, which is also quite popular. It's that we want to find an R code, which is a subset of our metric space, such that distance between any two distinct points in this code is at least some fixed number R. And then we say that this set X, it would be an R code. And of course, somehow there's two problems of finding good packing of balls and finding good R codes. They are closely related to each other, even though in some spaces, they might be a bit different. And of course, for the second version, our goal is for a fixed R to find this an R code with as many points as possible. And then many problems in mathematics can be phrased in this way. For example, as I already told you, the sphere packing problem in Euclidean space, the problem of finding error correcting codes. For example, if we take our space to be a Hamming space, and if we take our distance to be a Hamming distance, or it can be a question of independence number in a graph. When we have a graph and we say that the distance between 2 points is the smallest number of edges we need to cross to get from one point to another one. And so another problems, now we are coming closer to universal optimality. So another closely related problem is a problem of minimizing potential energy. So suppose that we're again fixing some metric space and we are considering a finite subset inside of our metric space. So now we can fix a potential function which is a function which is defined on the support of our metric and takes real values. And then we can define the potential P energy of this subset as this energy of, you can think of it as an energy of pairwise interactions between points in C. And here we assume that the energy of interaction, it will depend only on distance between 2 points. And so this definition here also somehow because now we have defined this P energy for finite sets, but in principle, if we work with Euclidean space, we also want to have this meaningful definition of P energy for infinite configurations, and therefore we are taking here this normalizing factor, so we are dividing by number of points. And so then this number, it would be, so to say, an average energy per one point in configuration. So when the number of points becomes infinite, we still have a hope that such a number would converge, and we would have a meaningful notion of energy. And so one issue with the specking problems and energy minimization problems is that they seem to be rather difficult ones, and this difficulty, it comes from, one could say, from their non-linearity. And so now I would like to tell you about one approach which allows us sometimes to analyze these problems, and in some cases, I should say rather rare cases, even solve them completely. And so here is the idea is to come from this problem of nonlinear optimization to formulate another question, to reduce it to a question in conic optimization. And conic optimization is much better understood, and here we have a lot of tools. Here we have a very convenient notion of duality. And so conic optimization, so classically we have a certain vector space, and this vector space we define a positive cone, which means that if we have 2 points in a cone, then any convex combination of these points again should belong to our cone. So here it's an example. Here is this famous ice cream cone, very, very nice one. And now what we are going to do, we want to we're studying linear functional on the points of this cone, and we want to find its minimum or maximum. And very often we are doing also this subject to some linear conditions, additional linear conditions. So here's our cone. This is our linear condition, and this is the functional we are optimizing. And so here there should be an extremum point, maximum or minimum. And so again, what is so nice about conic optimization is that there we have a well-defined notion of duality. And so for each cone C, we can always define its dual cone. So it would be a cone which exists in a dual space, or if we are considering a space with scalar product, then in our space itself. So it will be a space of all vectors such that their scalar product with all vectors in the cone is non-negative. And so here is a picture. So here, if we take this cone C, then its dual cone will look like this. And so when we are speaking about configurations of points on a metric space, then it becomes very natural to study this cone of functions, so-called copositive functions. So let, again, M rho be a metric space, and suppose that matrix has this, matrix rho has this support. Then we would say that the function f is copositive if the following sum is always non-negative. So we are fixing any finite subset in our metric space M, and we are considering a double sum over our pairs x and y in this set capital X, and we are evaluating function f at a distance between point x and point y. And so if we think of this in terms of energy potentials, so we see that for these copositive potentials, the energy has to be always non-negative. And so therefore such functions, they play a role in important role in physics and statistical physics, where somehow we don't want having configurations with negative energy. And so there is another also useful cone, so-called cone of positive definite functions, and it is a bigger cone. No, actually, it's a smaller cone because this condition is more restrictive. So here it's again a function which is defined on a support of rho, and we say that this function is positive definite if now such a sum is always non-negative. And here we also allow, now we are taking not just sum of these values, but we are also weighting it. So if now we are to each point in our finite set X, we are assigning some complex weight, Wx. And so now if now for this contribution, we are counting it with this complex weight. And so now what we require that now also all these doubles, all such double sums, they also have to be non-negative. And of course, it's clear that positive cone of positive definite functions, it's a subcone of the cone of copositive functions. And now a typical situation for interesting metric spaces rho is that the cone of copositive functions is very complicated. So there is no easy way to describe copositive functions. At the same time, usually the cone of positive definite functions is an easy one. And so you see this positive definite functions, they in some sense, they're similar to positive definite matrices. And positive definite matrices, this is a very nice set, very nice cone. We have very, very nice descriptions for it. It's easy to work with it computationally. And therefore, for proving optimality of certain configurations, it is easier for us to work with this smaller cone of functions. And so here's one theorem, which is actually very sounds like a very simple result, but very useful one. And so this is the way how we apply linear, so-called linear programming in geometric optimization. So this method was developed, I think, back in 70s and 80s. And so this principle works as following. So suppose that there exists a copositive function f, which satisfies these two conditions. It's that first, it's normalized so that its value at 0 is 1. And for if f of r is smaller or equal than -1 divided by n minus 1 for all r which are bigger than certain r0. So then we know that every r0 code in this in the metric space M rho contains at most n points. So this theory, so if so then knowing the copositive function f gives us a bound on the number of points in R0 code. And the proof of this theorem is very easy. So suppose that X is an R0 code. Then from the condition of copositivity, we know that this inequality should be true. On the other hand, if we are using these two conditions on function f, then we also obtain an upper bound like this. And because we know that these two inequalities, they cannot contradict each other. So from here, we know that this set X can contain at most n points. And this is a very nice result. So the only problem is that, as I told you, that describing the cone of copositive functions is very difficult. And then sometimes proving that arbitrary function is copositive, it's not easier than solving this problem here. On the other hand, in this theorem, what we can do, we can use a positive definite function. And so the positive cone of positive definite functions is too small. So here, the good thing is that it's easy to check that some function is positive definite. However, if we are restricting ourselves only to positive definite functions, then we don't have hope for sharp results in this theorem, or at least the sharpness of results is not guaranteed. And it occurs only in some rare cases, as we know. And so now let me give you some examples of these configurations for which this method still gives a sharp result. And as you will see that all these methods are somehow related to the Leech lattice and the E8 lattice. The first example, it's a Hamming code. So Hamming code, it's a code like this. So it's a subspace of 8-dimensional vector space over a finite field with 2 elements, and it's a subspace of dimension 4. And so this matrix, this is a generating matrix for this subspace. So it means that each row here, it's one vector in this space. And we also have take all their linear combinations, and then we will get all elements in this in the Hamming code. And we know that the minimal distance in the Hamming code is 4, and that the Hamming code contains exactly 16 elements. And of course, some of this is so now what we are going to see, that Hamming code is an optimal code of this size and with this minimal distance. And of course, this example is very small, so there are probably many proofs for this fact. It can be even done by hand, by brute force. But let's see how a theorem from the previous slide will work in this case. And so here it turns out that we have a very nice description for positive definite functions in Hamming space. And so this description is done in terms of so-called Kravchuk polynomials. And so how this works, so suppose that let's consider some vector y in our vector space, in this Hamming space of dimension n. And so let's consider this function fy. And it is, so here x dot y, it's a usual scalar product like this. And it's somehow from this line, it's clear that this function fy, it is a positive definite function. And so a Kravchuk polynomial, it's just averaging of this function over the Hamming distance. That's because this function, it depends not only on Hamming distance from x to 0, but we can average it over all vectors y of given Hamming distance, and then we will obtain what is called the Kravchuk polynomial, and Kravchuk polynomial will still be positive definite. And so we know that these functions are positive definite on this metric space. And so now we can prove that the Hamming, that if we have any set inside of Hamming space of dimension 8, and it's a code of distance 4, then it can contain at most 16 elements. And so in order to prove this theorem, we just need to present a function which would satisfy conditions of the theorem here. And so here one can present such a function. And so from this presentation, we see that it satisfies the conditions on the theorem regarding the values of f. And from this representation, we see that it is positive definite. And so now if it, so why did I tell you the story of a Hamming code? That's because we can use Hamming code and construct E8 lattice from a Hamming code. So let C be a code of distance D. Then let this be a, code in Hamming space of dimension n. We suppose that this code has distance D. Then let's consider the following set in Euclidean space. So this would be our code, and to this code we are adding the 2 times the integer lattice Zn. So from this description we already see that this set, it will be some periodic subset of Euclidean space. And we can also see that the point density of this set, it would be the cardinality of set C divided by 2 to the n. And because we started with C, we demanded first from C that it's a code. We know that the minimal distance between 2 elements in this set, it can be bounded like this. It will be at minimum of 4 and D, where D was the distance of our code. And also if C was a linear code, so namely if it was a subspace of the Hamming space, then it would immediately follow that this set is a lattice. And so now if we apply this construction A to a Hamming code, and so also rescale it a little bit, then we will obtain the E8 lattice. And what I will show you in the future, that the optimality of Hamming code can be proven by presenting a function with certain properties, even though that function was very simple. And the same property now is inherited by the E8 lattice. And actually, Leech lattice can be constructed in a similar way from a code in dimension 24. So this is a generating matrix of so-called binary Galais code, and it's a subspace of dimension 12 in Hamming space of dimension 24, and it has minimal Hamming distance 8. And so this is a proof which shows to us that Galais code is an optimal code with this distance and this number of points. And here again, the proof is analogous. So we prove optimality just by presenting a certain positive definite function which satisfies the conditions of our first theorem today. And so now, if we want to obtain a Leech lattice from Galais code, we have to work a bit more. So here we have to apply what Conway and Sloan call in their book on sphere packings, lattices and group, they call it construction B. So now we are applying construction A, but then we are considering 2 translated copies of the result of the set we obtain, and this is how we get a Leech lattice. So somehow its density is even bigger than what can be given by construction A, because it turns out that 2 copies of the same set can be fit into Euclidean space. And so now if we want to prove optimality of lattices, so we can use, again, the first theorem of today, only in Euclidean space it has to be modified a little bit. And so here a suitable modification was given by Henry Cohn and Noam Elkis. And so they have shown the following result. Suppose that there exists a Schwarz function defined on the Euclidean space of dimension n, such that this function is non-positive if the length of x is bigger or equal than certain fixed number r0, if the Fourier transform of f is non-negative, and so this condition, it replaces the condition of for function to be positive definite. And also we normalize our function in such a way that the value of function is 0 is the same as the value of its Fourier transform at 0, and it is equal 1. Then we say that each periodic for each periodic configuration X, such that the distance between any two given points is at most R0, then such a point configuration would have density at most 1. And so Kohn and Elkis have used this method numerically to estimate the sphere packing constant for different dimensions. And in the original paper, they did it for dimensions from 1 to 40. So here we denote by delta D the supremum over all possible densities in the Euclidean space. And so here this red line, this is their estimate, the numerical result they obtained. And the blue line is the best known density. And so we see that in most dimensions, these two lines, they don't match. So the red line, it gives us only an upper bound, and it's quite far away from the best known configuration. However, there are some exceptions. And so here from this plot, it's not very seen, but somehow these two lines, they do coincide at point 1, and they do coincide at point 2. But also what I wanted to talk about today is that these two lines, they coincide in point 8 and at point 24. And so in this paper from 2003, Kohn and Elkis, they did not prove the exact result. However, they proved a very impressive numerical result. So they've shown that even if there is a sphere packing in dimension 8, which has density greater than the density of the E8 lattice, so then it can be only this much. The improvement cannot be better than 1.00016. And in dimension 24, they could not exclude the possibility that there is an improvement over Leech lattice, but even if this improvement exists, it cannot be better than 1.019. And I should say, like, these numbers, they are from 2013, and since then there have been a lot of numerical improvement. And in 2016, I was able to find this Schwarz function, which satisfies exactly these conditions of the Kohn-Elkis theorem, and therefore I was able to prove the precise result that that in dimension 8 we cannot beat the density of the E8 lattice. And then same here, together with Henry, Abhinav, Steven, and Danilo, we have also proven same result for the Leech lattice. So we are able to construct this Schwarz function, which satisfies all these three conditions, and therefore satisfies all the requirements of the Kohn-Elkis theorem. And we prove, now we know that in dimension 24, Leech lattice is the densest sphere packing. And because these functions f(E8) and f(Leech), they prove sharp bounds for sphere packing, so therefore we call them the magic functions, because they do this hard work for us almost for free. And so this is the plot of these two of the functions f(E8) and its Fourier transform. So here on both sides they are multiplied by an exponentially growing function, because these two functions, they're Schwarz functions and they decay very fast. And if I don't multiply by this factor, then we would not see the behavior of function. And the behavior of function is that we see that this function, it vanishes, function itself, it vanishes at all square roots of even integers. And so at point 2, our function changes sign, and at all other square roots of even integers, it does not change the sign and has double 0. And same is true for the Fourier transform. Now the Fourier transform, it has double zeros at all square roots of even integers. And so this vanishing, it follows immediately from the sharpness of our bound. So our bound can be sharp if and only if the function has this behavior at all the lenses of non-zero vectors in our lattice. And so now it turns out that this information is actually sufficient to find the functions. And so here, when we want to find the functions, first we of course, what I draw you here, it's so in the theorem, my function, it was defined on 8-dimensional space, but what you can see here, it's only 1-dimensional. So how this happen? This happens because we assume our functions to be radial. So because all our conditions, they depend only on a distance of a point in Euclidean space to the origin. And it means that even if we had some non-radial function satisfying the conditions of Kohn-Elki's theorem, we could average it over all the rotations and obtain a radial function. And also some Poisson summation formulates another way to see that our function, so since our function has to vanish at all non-zero vectors of our lattice. And so now what I will, maybe you have some questions at this point. And if not, then I will maybe come closer to the construction. So how do we construct these two functions? And now we find these two functions as a certain, we give the integral representation for them. And so for both E8 lattice and Leech lattice, we will search for our function in this form. And so here, this representation, it will be valid if this radius R is big enough. So for dimension 8, R has to be bigger or equal than square root of 2. And for Leech lattice, R has to be bigger or equal than 2, so that this integral representation converges. And so here, this function phi lambda, it's a certain holomorphic function, which so we are integrating from 0 to I infinity. But our function phi lambda, it will be defined on the all upper half plane of the complex plane. And we say that this function phi, it also has nice transformation properties with respect to the action of the group SL2Z, which acts on the upper half plane by the Möbius transformations. But so now what we know from our function is that we want our function to have double zeros. So now maybe I will show you how to produce this double zeros and how to reduce, like what kind of nice transformations do we need from our function phi. So let's suppose that we can write our function in this form. And for a moment, somehow we forget about all the convergence issues. We assume that all the integrals do converge. And so first, what we can do, we can, of course, write sine as the sum of exponential functions. And now we can move this parenthesis here inside. And what we are doing now we are, instead of having this one, integrating over one contour like this, we consider 3 different integrals, one over this contour, one over this contour, and one over this contour. And so now what we will do next, now we are going to apply Fourier transform with respect to variable R to this function, which has this integral representation. And here, of course, we are using the fact that in our integral representation,
Lost sound, Maryna.
hello, can you hear me now?
We lost your sound for a couple of minutes.
And
Well,
okay,
a
and
minute, maybe.
so should I at which moment did you lose
The
my
penultimate line,
sorry?
but not the bottom line, the line above that, where you
Okay,
were
so
just talking
here
about the Fourier transform.
at this line.
Yeah.
Okay, good. Yeah, maybe I accidentally pressed something. Yes, so here we can apply, when we apply Fourier transform to this function, we see that in this integral representation, only this part depends on R. So we have to apply Fourier transform only to this complex Gaussian. And the action of Fourier transform on complex Gaussians, it is compatible with the action of modular group at the upper half plane. So if you apply Fourier transform to this Gaussian, then this is what we are going to get. And so, but now we want for our Fourier transform. So here our function f, it had this double zeros because of this term sine squared in front of the integral. And so now we want somehow the same to be true for the Fourier transform of f. But now, of course, because we have changed this exponential, the complex Gaussian here, things somehow we have ruined this sine squared. And so now we want to maybe impose certain conditions on our function phi, because function phi we still I didn't tell you what the function phi is. So maybe we can just choose function phi so that everything still works. And so now let's rewrite our integral. So here what I'm doing on this slide is just rewriting this integral, and want to, like, instead of this say transformed Gaussian, I want to get back this initial Gaussian I started with. And so here I'm doing just usual contour integral manipulations. So yeah, so one thing I do, I transform my contour. So I had these three contours like this, but now I'm transforming them into a, so here I'm choosing point I, and I'm transforming them into contour like this, into this chicken claw, which was on one of the previous slides. So this is what I do here at this step. And now I'm making a change of variables. And after I make a change of variables, this is what I will get. And hopefully I haven't made any mistake anywhere. And so now we are just rewriting what was in the previous slide. So this is what we get. But now you remember that what I wanted to do, I wanted to obtain this sine squared here. So now in order for this to work, I would have to make certain assumptions about these functions phi. And so now what I do, I simply request my function phi to satisfy these transformation rules. And it turns out that this system of equations, it can be solved explicitly, and it can be solved in terms of rather classical modular forms. And so after we can solve this explicitly, then we get also this representation for the Fourier transform of f, and therefore we are sure that Fourier transform of f also has double zeros in all the places where it needs to be. And so this is how we are able to prove the optimality for sphere packing. And so now in the remaining time, let me speak about universal optimality. And so now for this sphere packing problem, it can be rather naturally generalized in the following way. So here we if let C be some discrete and closed subset of Euclidean space, and let P be some energy profile, and then we can define lower P energy of C to be just this limit infimum. So so we are taking here this energy of finite sets, where our finite set, it's an intersection of our closed discrete configuration C with a ball of with center at 0 and radius r, and we take this radius to grow to infinity. And then for nice configurations, for example, such as periodic configurations, and somehow reasonably fast decaying P energies P, then such a limit would exist. And so if limit exists, we would say that EP, it's the P energy of configuration C. And also for this, for such a closed discrete configuration C, somehow we also need to define what is the density of C, because it makes this normally sparse configurations would have either bigger or smaller energies than condensed ones. So it makes sense to fix density to somehow to avoid trivial solutions of this problem. And so for this configuration C, we call this number a density of C. Of course, not for all discrete and closed subsets, this configuration is such a density would be well defined. But for example, it is well defined for all periodic configurations, and this class is wide enough for us. And so now we say that configuration C with density rho, it's universally optimal if it minimizes P energy for all P which are completely monotonic functions. So it minimizes P energy among all configurations of the same fixed density rho. And so completely monotonic functions are essentially for example, this real Gaussians, and also all convex combinations of real Gaussians. And so the theorem which we proved together with Henry Kohn, Abhinav Kumar, Stephen Miller, and Danilo Radchenko, it is that the lattices E8 and Leach lattice, they are universally optimal. So it means in particular that these lattices, they optimize all real Gaussian, they are optimal for all real Gaussian and energies. And maybe last thing I want to say is that this result, it also generalizes the result on sphere packing, because one can see sphere packing as a limiting case of this energy optimization problem, because it's not difficult to see that if certain configuration is optimal for all Gaussian energies, then it's automatically also optimal for the sphere packing problem. So thank you very much for your attention. So this is a short outline of my talk, and I will be happy to answer your questions.
Thank you very much. It was really fascinating to hear about. Any questions from the audience here?
I have a question.
Yes.
Is there any dimension in the lattice where this lattice solves the densest sphere packing problem, but is not universally optimal?
So I think we know very little about universal optimality. So actually in dimension 3, for example, for example, there are lattices which solve the sphere packing problem, but at the same time they are not universally optimal.
Okay.
Because about in dimension 3 we have this like phase transition. It's that if alpha is big, then solutions of sphere packing problem are optimal. In particular, for example, this phase central cubic FCC lattice, and but also together with this hexagonal closed packing and this incountably many other configurations. But then if this parameter alpha becomes very small, then actually the Fourier dual of FCC lattice will have smaller energy. Yeah, so therefore in dimension 3, we don't have seems like we don't have universal optimal configuration.
Okay, thank you.
Was it anybody in the Zoom audience? Thought, Peter, you might have your hand up.
Yeah, I have my hand up. Thanks. Thanks for a lovely talk. My question, in your construction of magic function, you gave no clue as to how SL2Z came into the picture,
Yes.
which of course is where how you came. I mean, I've heard your lecture before, and it's become much more transparent, all the features. So maybe you could comment on that. In other words, you've showed us the optimal, and you've convinced us it's correct, but maybe you can say a word of how you came about it and how SL2Z enters. I mean, that sort of is unexpected here, I would say, that the optimal function can be constructed through some modular type function or integral.
Yeah, so somehow, so I came through these equations, and somehow it's clear that all these equations, they are related to action of SL2R, and in particular even SL2Z. And yeah, so I think here there is some like moment of luck that that like nature is kind to us, and we did not need more complicated behavior from these functions. Yeah, so actually somehow, like if you write like all this, if you write down all these conditions, then we will see that, for example, this function phi, it's annihilated by a certain ideal in the group ring of SL2Z, and this ideal also turns out to be a rather nice ideal with simple generators, which is actually without many difficult relation conditions, and everything can be solved explicitly with rather simple functions.
Okay, thanks.
So good luck, I think, or somehow simple beauty. Any further questions? Okay, I think let's thank Maryna again for a really beautiful talk. So now we have a tea break, half an hour. I'm back here for 3:30 for the final session.